Okay, let's start. So let's still start with our example. So consider that price-size relationship. Okay, we have 12 houses. We know their sizes and we know their prices. Below, we will call the sizes as xi and the prices as yi. So that means they are labeled as xi and yi so that we can use symbols to deal with them. Okay, so basically when we get this set of data, the first thing that is very natural is to draw a scatter plot for them. Okay, so we can plot the 12 pairs of numbers to this scatter plot. We can see that seems to us that there is some kind of positive correlation. Okay, and it seems to us that the correlation should be high. As we already know, if we calculate the correlation coefficient, it's going to be around 0.729, right? So we want to use a good idea to relate sizes and prices so that we can use size to predict price. Okay? Or say it in another way, we want to find a line like this to be a best estimator or the best representation for this correlation. Okay, that's our target. We want to find such a line. Okay, so let's say how may we do that. When we say I want to identify a line, that means I am assuming that the relationship between the two variables is linear. Okay, if I assume the relationship is linear, or if I believe that the relationship is linear, then we are assuming that we have this formula. What's this? We are assuming that yi, the price of a house, is determined by a linear function of the size. Okay, beta 0 is the intercept of the equation, and the beta 1 is the slope of the equation. If you still remember that we are drawing a line to pass through the 12 points or to represent the 12 points, then beta 0 and the beta 1 can decide the line. Okay, can decide the line because that's the intercept and the slope of that line. Of course, in any case, in any real situation, this can be close to yi, but for many houses, this is not going to be precisely the price, right? There must be some deviation. There must be some deviation in practice. So we call epsilon I as a random noise for estimating record I. That means eventually we're going to get some estimates for beta 0 and beta 1, so that if I can get the size xi, I can plug in into this formula. I am going to expect that the price yi equals beta 0 plus beta 1 xi. Okay, I'm going to expect that to happen, but of course there would be some mismatch, and that mismatch is captured by epsilon I. So we know, we believe that somehow there is such a formula, somehow there is such a linear relationship, but we don't know beta 0 and beta 1. Okay, that means they are some parameters of the population, parameters of the population. And what we want to do is to collect sample data. Okay, for example, the information for the 12 houses, use the sample data to estimate beta 0 and beta 1. So actually this is a estimation problem, a statistical estimation problem. We want to use the 12 pairs of numbers to form two statistics. We call them beta hat 0 and beta hat 1 as our estimates of beta 0 and beta 1. They are parameters. They are statistics, just like they can be population mean, and we use sample mean to estimate population mean. Now our question is, given that we want to estimate the two population parameters, beta 0 and beta 1. How may we combine the information, the simple information we have to form these two numbers? And that's our question. Okay, so we know that if we have beta hat 0 and beta hat 1, we will use this formula to be our estimate of yi. We're going to plug in the size into this formula to get our estimation for the price. Okay, and then y hat I is called our estimate of yi. So that means we can now interpret epsilon I as another thing. It's our estimation error. Okay, because this guy is our y hat I. We know our estimation would be somewhat having a deviation from the true value. This is our predicted value. This is our true value. There can be some error, some differences. So we call epsilon I as our estimation error. For example, suppose someone suggests that beta 0 is 100 and the beta 1 is 2. Then this gives us a formula. So for each xi, this is our simple data. For each xi, I can plug in xi to calculate 100 plus 2xi. Okay, 46 becomes 192, 59 becomes 218, and so on. And once we have that, we can compare our y hat I with yi to calculate the difference. 24, 11, negative 23 if we are overestimating, and so on and so on. We can have all these numbers. Then obviously our task is to find two values, beta hat 0 and beta hat 1, so that these estimation errors can be minimized. Okay, can be minimized. We don't know how to do that. We don't even know how to define that. But intuitively, we want our formula to minimize these estimation errors. Okay, so that's our plan. So as another example, we may want to use a graph to represent what we did. So suppose the graph, the formula we want to use is 100 plus 2x. Okay, beta 0 is 100, beta 1 is 2. Then we are having a line like this. We probably would feel that, well, there are a few dots that are below the line. There are also a few dots that are above the line. So the line is not too bad. At least it's not systematically doing overestimation or underestimation. But for those points that the line overestimates, the difference is small. But for those points that the lines underestimates, we can see there are quite a few large deviations. So that means this line is not perfect, right? Ideally, this line should be moved upwards a little bit, so that those overestimation error and underestimation errors seems to be close to each other. Then that should somehow minimize the overall estimation error. So the graph can help us get this intuition, and that motivates us to look at some other lines. So how about this? Maybe we can say, how about 102.4? We increase beta 1 hat to be 2.4. Then the curve would be somewhat different, something like this. Okay? And then, now we say, well, not too bad. But now, when the line underestimates a point, the deviation is not so large. But when the line overestimates, then we have a lot of estimation error. So it seems to us that we move the curve upwards too much. Moreover, we are not just controlling beta hat 1, right? We may also modify beta hat 0. So there are a lot of possibilities, and there is no way for us to try all these numbers. So we need to first define a measurement for estimation, define a way to aggregate all the errors. Okay, and then we need to have an efficient way to find beta 0 and beta 1 to minimize that overall error. In the next video, we tell you how. Thank you.